get a little practice with calculating torques. This is problem number 1077. And so what we're going to do is we're going to look at the torques for each of these forces. So force 1 is 3 newtons, force 2 is 2 newtons, and force 3 is 3 newtons, and force 4 is 1.8 newtons. And we're going to need to pay attention to the direction of rotation that each of these contribute to. Notice that force 1 causes a rotation in this direction, as does force 4, right? But force 2 is causing a rotation in the opposite direction. So if we like a rotation in this direction, if we use our right-hand rule, that would be an omega and an alpha into the page, and F2 would be out of the page, okay? So we're going to kind of keep track of those, the into and out of the page. So out and into the page. So into would be in the minus k hat direction, and out would be in the plus k hat direction. And you can check by doing the cross products that this is still the case. Okay, so what we're trying to find is the net torque, the total torque. And so I didn't say anything about F3 because the torque associated with F3 is actually equal to 0. The torque is equal to 0 because there is no moment arm, there's no R. So if you do R cross F, if R is 0, you get a torque 0. So that's for number 3. Okay, so for torque for number 1, torque 1, so torque 1, since this is 90 degrees, this is just going to be 3 newtons times 3 meters times the sine of 90 degrees. This is the magnitude of the torque. So the torque is just equal to 9 Newton meters. Now I know Newton meters is what we usually write as a joule, but to remind ourselves that this is torque and it actually is a vector, we always use torque as Newton meters or foot-pounds. We don't turn it into an energy form, even though those are the same units, because torque is a vector and energy is not. So joules are associated with non-vectors. So this is just a way to remind ourselves that this is torque. Okay, so that's torque for 1. And then torque for 2, notice that we've got this angle here, so we can sort of redraw what we've got. Here's force 2, here's the radius, the R of 2 meters, and the angle between them is now 30 plus 90, or 120 degrees. So we can say that our torque 2 is F2, 2 newtons, times 2 meters, times the sine of 120 degrees. So torque 2, the magnitude of it, is 4 times sine of 120, which is 0.866. So this gives me 3.46 Newton meters. And then for torque number 4, so torque 4, we do the same kind of thing. We've got our force 4, which is 20 degrees. And then, so altogether, this is 20 plus 90, or 110 degrees. This is 2 meters. Force 4 is 1.8 newtons. So torque 4 is going to be 1.8 newtons times 2 meters times the sine of 110 degrees. So torque 4, when I calculate that out, gives me 3.38. This is again the magnitude, Newton meters. So altogether, we have into, in the minus k hat, we have 1 and 4. So that gives me 12.38 Newton meters. We have torque in the minus k hat direction, so that would be in minus k hat direction. And then over here, the torque that's pointing out in the plus k hat direction, torque out, is 3.36 Newton meters and the plus k, when we add these together, our net is going to be in the minus k hat direction, and that gives me our total is 8.9 Newton meters in the minus k hat direction. And that is our total torque. So this is sort of just an artificial problem, but I wanted you to see how we use these, and notice that what I do in order to find the angle between these two is I go ahead and line them up tail to tail so that I can find the angle between them.